Good morning, everybody, and welcome to the CEIA Maths Tutorials Online. Welcome to the Sequences and Series tutorial, which will be given by Suzanne O'Callaghan. Okay, so over to you, Suzanne.
Thank you, Eamon. Good morning, everyone. As Eamon said, Suzanne O'Callaghan is my name. I'm a biomedical engineer and I work in Tyndall National Institute in Cork, and that's attached to CIT and UCC. So I've been kindly asked by CEIA to give this lecture this morning on sequences and series. But I'm also asked to say a few words on how maths is used in my everyday life as an engineer. Right, so as I said, how do I use maths in my everyday life as an engineer? Well, pretty much as an engineer, I use it every day. Basic calculations, use a calculator every day. But for some jobs, I have to use more advanced maths, like for instance, calculus, area and volume. So an example would be, I am currently working on a smart wound dressing. So I have embedded electronics into a dressing that detects if the wound is bleeding, if there's infection there, if there's a problem that somebody needs to get alerted via a smartphone or a computer. But my problem initially starting off is I need to track how fluid moves through the foam. And you know, foam is, a square little piece of foam, which you'd see in any dressing or any plaster, has a lot of holes in it. So that would be very similar to a lot of the questions you do, where you do volume of a cube or a cylinder, and within it is dropped a sphere. So that would be an example of how I have to work out how much fluid is in the sponge and how much air is in those gaps. So for that, I would be using the area and volume initially, and then I would have to start using calculus to differentiate and find out the rates of change. In other words, the rate of the moisture filling the pad, so that I would get an indication to say that the dressing is full or it's half full. In other words, it's reached full volume or half volume. So it's things like that I would use it for. But as I say, you wouldn't be using it for intricate maths every day. But a lot of the basic maths you'd use as an engineer. So just a little background into myself. I'd like to say that I wasn't very good at maths when I was in secondary school. In primary school, I had no issue with maths. I was very bright, picked it up very quickly, as I'm sure all you do as well, given that you're all doing honours maths. But I did find when I got to secondary school, there was a bit more effort needed. There was concepts that were being thrown at me. There were X's and Y's coming in. There were formulae that needed to be learned. And this wasn't the maths that I was used to. So I didn't apply myself very well. And I barely scraped through with a C in honours maths my junior cert. But, and then I passed into fifth year honours maths. And I spent that year failing everything. I mean, I was getting maths tests back at 10, 11%. But I had a lucky break in that I repeated fifth year, and I got a different teacher, a teacher that I had previously for another topic, and she scared the bejesus out of me. She really was one of those teachers that you always had your homework done. So she made me work mainly because I was afraid of her. And she also had a competition every day whereby she had this thing where she'd ask questions every morning. How far did you get in the maths questions? So she would set maybe 4 questions, and then she would say, continue on after that and go as far as you can. So every morning she'd ask the question, how far did you get? So she'd say, who got to 5, who got to 6? And you'd see all the hands go up until she'd get to 8 and 9, and the hands would start to drop. And there was this one particular girl, a genius, I'm sure you've all got them in your classes, whose hand was always up to the very last. And this used to drive me nuts. So I used to go home at night, finish my homework, and then open up the maths books and start doing as many questions as I could. I mean, sometimes I would spend 2 and 3 hours into midnight trying to go as far as I could into the really difficult parts of the questions, and I'd still come in next morning and she always had her hand up after me. So one day I was the last person to have my hand up. It's because she was out sick, so it didn't really count. So the point I'm making to you from that story is that you don't necessarily have to be, a genius at maths. Most of us aren't, but how you can become really good at maths is by working really hard at it and by practicing it and by doing a lot. And I discovered unintentionally I was motivated competition wise. I just wanted to beat her. But by doing that, I actually learned an awful lot about maths. I got really, really clever at it. I got really astute at understanding questions very quickly, and it meant that I improved vastly. So the point I'm making to you all, it's really important. You don't have to be very good at maths to be an engineer, because you learn all those skills in college. And the way to be really good at maths is just to do as much as you can. So I'm going to go through sequence and series today. I'll do the first 10 or 14 slides will be the introduction into all the different topics of geometric series. Our sequence and series. I hope that you'll ask questions. All the slides are numbered. So if you want to ask a question, refer to that numbered slide. If you want me to go back on a slide and go through the topic that I've already discussed, or if there's something you don't understand, or if you notice a mistake, please don't hesitate to ask. Because by asking questions, you're actually making the session much more interactive, much more interesting. And I guarantee you 90% of your colleagues will be thinking the same thing, or a lot of them mightn't even have thought of the question and will think, wow, I didn't even think to ask that. So please do, it'll make the session much more interesting. I hope you enjoy it. And at the end of the session, then we'll do some exam questions. So I'm going to turn off my video simply because I find that it's a distraction. With maths, you really need to focus on what's going on the screen. So I'm going to turn off the video, and but you'll hear my voice. Okay. So I hope you enjoy it. So sequence and series. What we'll cover in today's topic is, the first thing is the introduction, a general introduction to sequence and series. I'll go through the notation and terminology, which is really important with regard to sequences and series, because it can get very confusing with the formulae, with S's and T's and N's. So I just want to clarify all that for you today. We'll go through the sequence formulae and which ones need to be applied where. The limits of sequences, it comes up in exam questions, so it's important to understand it. The arithmetic, so these are the next three, are the different types of sequences that are there. You've got the arithmetic ones, you've got the quadratic ones, and the geometric ones. And you will be asked in exam questions to identify if a sequence that they present you with is arithmetic, quadratic, or geometric. And then at the end, now through all of these topics, I will do examples at the end of each. And at the very end, if we have time, we'll go through actual exam questions. And I've chosen ones that actually are very good in the sense that they have covered a lot of the topics in the question. So the general introduction is, sequence and series are all about patterns and building patterns. You can see there, I'm sure you're used to seeing all of these in your textbooks. So you see patterns in terms of shapes, but we can also convert patterns to numbers, as in how many, let's say if you look at the top right hand corner and you see those orange and yellow cubes. So the first term has 2 cubes in it, 2 Lego pieces. The next term is 4 and the next term is 6. So it's obvious 2 are being added on every time. Again, down at the bottom, you've got the yellow blocks. You've got 1, 2, 3, and 4. But those are the terms. That's term 1, term 2, term 3, and term 4. So term 1 has 1 square. Term 2 has 4 squares. Term 3 has 7 squares. And term 4 has 7, 10 squares. So what you'll be asked for is either to find what term has a certain number attached to it, or they'll give you a number and say, tell us what term that is. Or they'll also give you a term and say, how many dots or shapes are in, or units are in that pattern. So you see there the triangles, the top left-hand corner. Again, the triangles get bigger and bigger, but you can also count the number of dots. So we'll say, for instance, term 5 has 15 dots. If I'm going too fast as well, please pass a note to the modulator and they'll let me know. So the typical notation is a sequence can be referred to as T, U, or A. For instance, you can have T1, T2, T3, T4, and T5, U1, U2, U3, or A1, A2, A3, A4. Now, we will find later on, for those of you who have covered the topic already, that A is also known as the first term. So it can get confusing if in the exam, and they have done it, they say to you, this sequence A is A1, A2, A3, A4, and A5. And you may get confused, you may get mixed up because you already have an A for the first. So it's just a matter of, in your own mind, separate the A's. The A1 and the A2 and the A3 is just a replacement for U or T, okay? It's just a way of naming the term. So if U is 5, 8, 13, 20, then U1 is going to be 5, U3 is going to be 13, and UN, which is called the general term, is a term indeterminate. We don't know what number it is. Now, with regard to the UN, the term before the nth term is known as U of n minus 1. And the term after the nth term is U of n plus 1. It's very important to understand that terminology because a lot of the formulae for a term will include a previous or a following term. So a typical formula would look like T of n is equal to n squared plus 3n. So then T of 1, which is first term, would be, you substitute in 1 for everywhere you see an n. So T of 1 would be 1 squared plus 3 times 1. My apologies, there's an n in there. That's an error, that shouldn't be there. So it would be for T2, or sorry, for T99 example, it would be 99 squared plus 3 by 99. So wherever there's an n, you replace that number in the formula. Simple as that. So we'll do an example. So the first two terms of the sequence U of n are an plus b. So that's a formula that you've been given. And they are 7 and 11. Find the value of A and the value of B. So for the solution, they've said that U1 is 7. And we know the formula is U of n is equal to an plus b. So we just substitute in n into the formula and we get a by 1 plus b is equal to 7. So then a plus b is equal to 7. So that's our first equation. We also know that U2 is equal to 11. They've given us that. So you substitute in 2 for n into the formula and you get A2 plus b is equal to 11. So 2a plus b is equal to 11. That's your second equation. Now, obviously what you're going to do next is you got your two equations in two variables. By variables, I mean a and b. And the reason they're called variables is because they can take on a varying number of values. For instance, what's a constant? A constant is something that's always the same number. It's constantly the same number. So what's a constant? An example? 1, 2, 3, 4, 5. A number is a constant. In other words, 2 never changes. 2 is always 2. But A can change. A can take the value of 10 or 20 or 5. So the first equation, what we do is we multiply it by -1 and we get minus A minus B is equal to -7. Second equation, we leave it as it is. 2a plus b is equal to 11. We add them together or subtract them as you want to say. And it gives us a is equal to 4. Therefore, b is equal to 3. Thus, U of n is equal to 4n plus 3. So that's actually the formula for this U sequence. So I'll leave you looking at that for a second. Okay, we'll move on. So the next formula that you have is what's called a recursive formula. Using a recursive formula, you can find a sequence from the term or terms that come before it. In other words, a recursive formula is based on terms that already are given or known. But you must be given some initial terms. You can't find the formula unless you already have some initial terms to go on. So for example, a sequence may be described by this recursion formula. So the recursion formula is u of n plus 2 is equal to 2 times u of n plus 1 plus u of n. Now, can you see what's recursive about that? It's that u of n plus 2, the value of that is calculated based on knowing the term before it and the term before that. In other words, it's based on knowing u of n plus 1 and based on u of n. That's what's called a recursive formula. So you can calculate the formula based on terms you already know. So they've given us here now the initial terms that we need. And the initial terms are u of 1 is equal to 0 and u of 2 is equal to 0.5. So that's good. That's a start. So it follows then that we know that for n is equal to 1, that gives us u3. Because remember, if you look at the formula, u of n plus 2, so you sub in for n, so that gives you u of 3 is equal to 2 times u of 2 plus u1. Remember, I'm substituting in 1 everywhere there's an n in the formula. And that gives us 2 by 0.5 plus 0 is equal to 1. So that's telling us that u of 3 is equal to 1. And we were able to calculate it based on knowing u1 and u2. So the next one is where we have n is equal to 2. That gives us u of 4 because it's n plus 2. So that's 2 plus 2, so that's 4. So u of 4 is twice u3 plus u2. Again, it's based on the values of the combinations of the previous terms. So it's 2 times 1 plus 0.5 is equal to 2.5. So we now have solved for u of 3 and u of 4. Now, another thing to note is that recursion formula could also be written as u of n is equal to twice u of n minus 1 plus u of n minus 2. So if you look at the formula, you can see that u of n is based on twice the term before it plus once the term before that. So just because you've changed from n plus 2 to n, you'd alternatively alter the u terms in the formula. So it can be written that way as well. Okay? So we will go on and do an example. If you bear with me. Okay, so example 2 here. So the diagram below shows the first 4 patterns in a sequence. Each pattern consists of a number of nodes joined by line segments. The sequence u of n gives the number of nodes in the nth pattern. So it can be shown that u of n can be given by the recursion formula u of n is equal to u of n minus 1 plus 3n minus 2. That is the recursion formula. And that is so only if n is greater than or equal to 2 and u of n is equal to 1. So u of n is your initial term that they're giving you. Use this formula to verify the values of u2, u3, and u4. So it wants us to verify the values of u3, u2, u3, and u4. Now, that's to verify them, but let's write them down ourselves first. What's the value of u1? So this is u1, and its value is 1. This is u2, and its value is 1, 2, 3, 4, 5. 5. What's u3? its value is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Am I right here? I got 3, 6, 7, 8, 9, 10, 11, 12. So it's 12. And u of 4, we're going to calculate. I have it here written down, 22. Okay, so we're going to verify those values. So they've told us that u1 is equal to 1. That's a given. So we're going to use u of n is equal to u of n minus 1 plus 3 of n minus 2. So when n is equal to 2, u of, remember, 2 minus 1 plus 3 by 2 minus 2 is equal to, apologies, is equal to, so u of 2 minus 1 is u of 1. And we know that u of 1 is 1, plus 3 by 2 is 4, minus 2, plus 3 by 2 is 6, minus 2 is 4, that's 4, which is equal to 5. So u of 2, u of 1 is u of 2 is equal to u of 1. Yes, u of 2 is 5. Okay. The next one we do is n is equal to 3. So u of 3 is equal to u of 2 plus 3 times 3 minus 2 is equal to 5 plus 7 is equal to 12. Again, correct. And we have n is equal to 4. We have u of 4 is equal to u of 3 plus 3 by 4 minus 2 is equal to 12 plus 10 is equal to 22. And again, that's correct. So if you didn't have those numbers, you could work them out based on the recursive formula that you've been given. So this is your recursive formula here. Okay, and this is your initial term that you were given. Part 2. Let's see. So what are they asking for in part 2? The sequence u of n can also be given by the formula u of n is equal to 3n squared minus n. Use this formula to find the number of nodes in the 10th pattern. So they've given us another way of writing the recursion formula, which is u of n is equal to 3n squared minus n is equal to 2. So basically, they have given us okay, sorry. So they've given us two formulas for the to find the value of a term. So why would we use this formula and not the other formula for 10 to find the 10th pattern? Sorry, my pointer. Okay. So why would we not use this formula? The reason being is that to find U10, we would need to know U9. We don't have U9. We'd have to work it out step by step, you get using N to N3. But using the formula, we only need to know the value of N. So it would be inputting the N, we'd have 3 times 10 squared minus 10 all over 2 is equal to 145. So that's how we can work out the value, the number of nodes in unit 10. So what I want to highlight here is when I mentioned that the formula that we were given here, the recursive formula, u of n plus 2 is equal to 2 times u of n plus 1 plus n. It's for n greater than or equal to 1. Why is that? Because, yes, the point being is that you can't have a 0 term. If n isn't greater than or equal to 1, in other words, if it's 0 or negative, you can't have u of 0 because it doesn't exist. The first term is always u of 1. So similarly, down at the bottom of the screen, where you see an alternative way to rewrite the formula as u of n is equal to 2 times u of n minus 1 plus u of n minus 2, you have to be careful there that you make sure that n never goes below 0 in the subscript. So for instance, the lowest term there in that formula is u of n minus 2. Say for instance, if n was 2, had a value of 2, then you'd have 2 minus 2, so you'd have u of 0 again, you can't have. So that's why those provisos are in there, that n has to be greater than or equal to a certain number. It's only to ensure that your terms begin at 1, U1, U2, U3. So the limits of a sequence, right? The limit of a sequence U of n is the number that the terms of the sequence approach as n increases without bound. In other words, as n increases or approaches infinity. But you must note that not all sequences have limits. For example, you have a sequence here which is U of n is equal to n over n plus 1. And the terms of the sequence are 1/2, 2/3, 3/4, 4/5, 5/6. But you can see it's started at 1/2, but it's now up to 99 hundredths. You're getting very close to the value of 1. Okay? So that's how a sequence changes. And as n gets larger, the terms, each term gets closer to 1, as you can see there. Thus, the limit of u of n as n approaches infinity, in other words, as n gets bigger and bigger and bigger, or you can also say the limit of n over n plus 1 as n approaches infinity is equal to 1. So, to calculate the limits of sequences, there are a couple of special limits that you can make use of. In other words, these are limits that you will know of and you can use them into your calculations. You don't have to prove them or derive them, you just have to know them. The first one is the limit of k over n to the power of p as n approaches infinity is equal to 1. K has to be an element of R, of the real numbers, and P has to be greater than 0. Why is P greater than 0? For instance, if P was less than 0, then you'd have n to the power of minus 1. Well, then it's going to get smaller and smaller and smaller. But if P is greater than 0, you're going to have n getting bigger and bigger because it's going to be n to the power of 1, to the power of 100, to the power of 1,000. It's getting huge. And the other one is that the limit of r to the power of n as n approaches infinity is 0. But this is only the case when r is less than, is in between, is greater than -1, and it's less than, it's greater than -1. Actually, I must correct that, and less than 1. Why is that? If r is a fraction, then if it's between 1 and -1, it's maybe a half. So if you have r to the power of a half by r to the power of a half by a half by r to the power of a half by a half by a half, that fraction is getting smaller and smaller and smaller. So when you have a sequence where it's to the power of a fraction, it's converging to 0, or it's diverging to 0. Okay, so it's approaching 0. That's the limit of it. It's approaching 0. Those are two very important special limits that you need to remember. Write them down and memorize them. So the procedure for calculating the limits of sequences, very common in exam questions. First of all, the first thing to do is divide above and below by the dominant term. So your dominant term there is n squared. That's the biggest one. The next term would be n. So if you divide above and below by it, you're left with 5 plus 4 over 2 minus n over 1 over n plus 6 over n squared. So we'll do an example to explain it. Is this still visible? Is that screen still visible, Eamon? Perhaps you could...
It is, yeah, no
Great.
problem. All good,
Okay.
Suzanne, thank you.
So we have example 3. Evaluate the limit as n approaches infinity of n squared minus 4n plus 5 over 3n squared plus 7. So again, you divide above and below by n squared because it's the highest power of n. And then you use the special limit 1 that I mentioned. So we have, yeah, so we'll carry on from here. So it's the limit as n approaches infinity of 1 minus 4 over n plus 5 over n squared. So you got to divide everything above the line by n squared and everything below the line by n squared. So that's 3 plus 7 over n squared. Okay? So we've got to evaluate that limit now. So that's equal to the limit of, let's evaluate each one of those. As n approaches infinity of is equal to, okay, so the first part, the first one here, what's the limit of 1? Well, the limit of 1 is 1, it never changes. What's the limit of minus 4 over n as n approaches infinity? Think of it. If you have 4 over n, and that goes to infinity, 4 over infinity, imagine 4 over 1 billion. Billion. It's so minute of a fraction. As n is below the line and it gets bigger and bigger and bigger, 4 of n actually becomes valueless. It becomes a tiny, tiny dot of a fraction. Same happens with n squared. So it's 5 over infinity squared, which is going to be 0 as well. So they actually end up having a limit of 0. Under the line, so we have 1 minus 0 plus 0. And under the line, what's the limit of 3 as n approaches infinity? Well, 3 has nothing to do with n, it's just 3, so it stays at 3. And then what's the limit of 7 over n squared as n approaches infinity? Well, again, if n becomes infinity, that's 7 over infinity squared. That's nothing, it's effectively 0. Okay, so you're left with 1/3. So that's the limit of n squared minus 4n plus 5 all over 3n squared plus 7 as n approaches infinity. Simple as that. So, how to find the limit of a sequence by a recursion formula? Sometimes they have a limit. And if it does have a limit, the recursion formula can be used to find that limit. So the method for finding the limit is based on the fact that if the limit of u of n as n approaches infinity is u, then all the other terms have the same limit. In other words, the limit of u of n plus 1 as n approaches infinity is u as well. It's the same as the limit of u of n plus 1,000 as n approaches infinity is u. Okay? So again, I've highlighted the points that you need to remember, and they're the ones that will help you in solving your questions. So it's an example 4, and it's a question for the sequence u. And u1 is the initial term that we're given. U of n plus 1 is equal to un squared plus 2 all over 2 times u of n. So we're asked to find the limit, the value of u, if the limit of u of n is equal to u, all the values of u greater than 0. So what we did first was we know that if the limit of u of n here will help. So if the limit of u of n is equal to u, then we know for a fact by previous slide that the limit of u of n plus 1, in other words, any other u, any other term in that sequence is going to be equal to u. So we can use that. So what we do is we take the limit of both sides of the equation. So we have u, and it's this equation here that we were given. So we take the limit of both sides of it. So we start with the first part here, u of n plus 1. What's the limit of that? Well, we know it's u. What's the limit of u of n squared? Well, we know that the limit of u of n is u, so that's squared, so that becomes u squared. And then it's plus 2, the limit of 2 is 2. And under the line, we know that the limit of u of n is u. So under the line, we have 2u. So we just evaluate it. 2u squared is equal to u squared plus 2. So that gives us u squared is equal to 2. So u is equal to the root 2 as u is greater than 0. So for all values, u is equal to root 2. So progress on to... I'm just wondering when I bounce back to the PowerPoint, is that not maybe right? So that was example 4 that we did there. Move on to the next page. So now what we're working on, we'll finish our arithmetic sequences before the break, take a break for 10 minutes, and we'll come back to the quadratic and the geometric sequences. So an arithmetic sequence, here's the definition of it. It's a sequence in which every term after the first term can be constructed from the previous term by adding on or subtracting the same fixed constant. Example, the sequence here is 3, 7, 11, 15. So what have we done in that? We've added on 4 onto every single term. So how do you identify an arithmetic sequence, which you'll be asked to do in an exam? Well, you find the constant first differences. Example, we've got a sequence here, 2.7, 4.1, 5.5, etc. And I've just spread them out, and they're all the terms. So 2.7 is term 1, 4.1 is term 2, and so on. The first difference between them is 1.4, and as you can see, it's constantly 1.4. So it's a constant difference, which means it's an arithmetic sequence. So the general definition for an arithmetic sequence is that Tn minus Tn minus 1 is equal to constant. In normal terms, what that means is term 3 minus term 2 is going to give you a constant number. And for all n is greater than 1. An arithmetic sequence formula, it must be linear and of this form. Tn is equal to Pn plus Q, where P and Q are constants. So that's your typical formula for an arithmetic sequence. Okay, so we're on to example 5. So the question is, prove that the sequence T of n, which we're now calling a T sequence rather than a U sequence, and it's 5n plus 2, prove that it's arithmetic And secondly, prove that the sequence u of n is equal to n squared plus 1 is not arithmetic. Okay, so that's our first job here. So as the formula for t of n is linear, you know that the sequence is arithmetic. I mean, the formula is linear. How do we know it's linear? What does it mean by linear? So the formula t of n is equal to 5 of n plus 2. How do we know it's linear? Because n is actually a single power. If it was n squared, it would be a quadratic. N cubed, it would be a cubic. But it's a linear function. So, but to prove it, you have to use the definition. So you have Tn is equal to 5n plus 2. So Tn of minus 1 is equal to 5 times n minus 1 plus 2 is equal to 5n minus 3. Now we have to take them, we have two terms there, one after the other. So in order to verify it, we have to test if Tn minus 1 will give us a constant. So will it? So the first one is 5n plus 2 minus 5n minus 3. Remember, this is t of n and this is t of n minus 1. And the answer there is 5. So it's a constant. So it's arithmetic. That's it. That's all you have to do to prove it. Simple as. If you were actually given a sequence with all those numbers, just subtract two lots from each other and prove that the difference is a constant number. Okay, so these are the terms in our arithmetic sequence. So the general terms for it are that the first term, a, is a, and it's a or t of 1. Common difference is known as d, and that's equal to t2 minus t1, which is just what we did previously. And the formula for it is t of n is equal to a plus n minus 1d. So these are the most important terms that you need to understand when you're calculating arithmetic sequences. So we have an example here again. Right, so we have an arithmetic sequence. The fourth term is 15, and the 11th term is 3 times the third term. Express t of n in terms of n, and then find the value of t of n find the value of n if t of n is equal to 852. Okay, so we have the fourth term, t of 4, they've told us, is 15. The 11th term, t of 11, is equal to 3 times the third term, t of 3. Okay? Now, how can we express t of 4 differently? We know it's equal to 15, but it can also be expressed in terms of t of n is equal to a plus off my general term. So what did we say? A plus n minus 1d. So that's going to give us a plus 3d is equal to 15. That's your first equation that you created. T of 11, we know, is equal to 3 times T3. That's equal to a plus 10d. And that's equal to 3 times a plus 2d. Now, where did all of that come from? Well, a plus 2d we know that t of 4 is a plus 3d is equal to 15. So we have 3 times a plus 2d is for t3. So that's t3, that's 3 times it, and that's t11. Okay, this is T11. Remember, A plus n minus 1 d. So that gives us minus 2a plus 4d is equal to 0, and that gives us minus a plus 2d is equal to 0. So you solve it simultaneously. There's your other equation there, second equation. Okay, so I'm not going to do that on the board because I want to focus on the sequences topic. So you solve that simultaneously and you get a is equal to 6 and d is equal to 3. So that means T of n, which we know to be T of n is equal to a plus n minus 1 d. We know it now will be 6 plus n minus 1, 3. So T of n is equal to 3n plus 3. That is your formula for evaluating that sequence. Okay? So we continue with the sum of terms, and this is where you add up all of the terms in a sequence. And that is referred to as S of n, for sum. So S of n is equal to T1 plus T2 plus T3 up to Tn. And the sum formula, which is in your tables, is S of n is equal to n over 2 times 2a plus n minus 1d. On to example 7. So for example 7, they ask you find a formula for the sum to n terms of the arithmetic series. And it begins with 2 plus 8 plus 14. And then it says use the formula that you work out to evaluate 116 plus 122 all the way up to 266. So for the arithmetic sequence, for the arithmetic series, what do we know? A is equal to 2. What's the common difference? D. D is equal to 8 minus 2 is equal to 6. Or it's 14 minus 8 is equal to 6. So there's your common difference. So then for our formula, we're asked to find the sum to n terms. That means S of n. So S of n, we refer to our tables, and we have n over 2 times 2 times 2 plus n minus 1, 6. And that's equal to n over 2 times 6n minus 2. So S of n is equal to n times 3n minus 1. And you could leave it at that, or you could multiply it in if you wanted to. Okay, so that's the answer to the first part. Second part is use this formula to evaluate 116 plus 122 plus 266. Okay, so that's the formula that we've been given. And to evaluate that formula, we have, so what they've given us is 116 plus 122 plus whatever happens in between plus 266. And we know that is equal to 2 plus 8 plus dot, 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 all the way up to 266. Minus 2 plus 8 plus dot 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 plus 110. Okay, so you need to find out which terms correspond to 110 and 266. So for our series, we have T of n is equal to 2 plus n minus 1 times 6 is equal to 6n minus 4. Then we have 6n minus 4 is equal to 110, which tells us that 6n is equal to 114. Therefore, n is equal to 19. So we know that that 110 occurs at term 19. So the second one is, so on part 2 here, we need to identify what term 266 is. In other words, 266 there and 110 there. So that's term, we've established term 19, and this term we want to know what it is. So we have 6n minus 4 is equal to 266, because this is the sum of. And we need to solve for n. So 6n is equal to 270, n is equal to 45. So that tells us that 266 is term 45. Therefore, thus, we have 116 plus 122 plus 266. That's equal to S45 minus S19. And that gives us 45 times 3, 45 minus 1, minus 19 times 3 into 19 minus 1. Bear in mind that these are S of 45 and S of 19. And we calculate that, we get 45 times 134 minus 19 times 56 is equal to 4966. So to recap, we're asked for, use the formula that we found to find the sum to n terms of the arithmetic series 2 plus 8 plus 14. Okay? So in other words, they're saying we can use that same formula to evaluate 116 plus 122 plus 266. The problem is that the issue we faced was that we want to know the sum from 116 up to 266. Okay? But if we work out the formula for S of n, it sees n as 266. Remember here the formula for S of n. And that will give us, if we use that formula directly there, it would give us the sum of all the terms from 266 all the way back down to 2 plus 8 plus 14, remember? So this formula that we've worked out is to work out the sum of these starting at 2 up to T of n. So for us to evaluate up to this term here, 266, we don't know what term it is. In other words, how many terms is it after the very first? So what we do is we evaluate the whole, the sum of S66, the sum of 266, which takes in everything from 2 all the way up to 266. So it's basically adding up from everything up to 266. But we also get the sum up to, what's the previous term before 116? It would be 110, because 6 is our common difference. So we then also get the sum of everything from 2 up to 110, and we take it away from this one to only be left with from 116 up to 266. So I hope you understand why we weren't able to go straight in and plug the 266 in here, because it would have given you the sum total of all the series starting at 2, because that formula is based on A, your first term is 2, and D is 6. So to recap, we had to get the sum of everything up to 266, but also get the sum of the sequence up to 210 and subtract it from the 266, which is what we did. We just inputted our information here, down here in part 2. So there is what we're looking for, just from 116 to 266. But we had to evaluate from 2 up to 110 and from 2 up to 266, separate them, and what's left then is our value. So we did that. We found out what term they were, and 110 was term 19, 266 was term 45, and we did S of 45 minus S of 19. And again, just plug all the information into your formula and you get 4966. Okay, so we'll take a break and we'll return in, we'll say at 11:30.
Welcome back, everybody, to the CEIA Maths Tutorials Online. Welcome back to part 2 of today's tutorial, sequences and series 1 and 2.
I'll tell you what I'm going to do, because there seems to be a problem that, yeah, the whiteboard wasn't always switching over. So what I will do is at the very end of the session, I will go back and I will just literally run through each of them without speaking, but leave the example up for a few seconds so people then can pause it and look at it afterwards when they go back at it. But every single example that was worked out will be at the end of the session. I'll do each whiteboard page, there's about 15 pages there, and they can look through them all then, so they'll see all the workings. So we finished up on the sum formula. There was we did example 7. I won't do 8 because it's similar enough to 7. We'll go on to quadratic sequences. So a sequence is quadratic if the first differences between successive terms are not constant. So remember the arithmetic terms, it is constant. The second differences are constant, so you get a second difference. So the formula for it is T of n is equal to an squared plus bn plus c. A, B, C are constants. Now remember, if you think of the previous one for the arithmetic, you could remember that the n didn't have any power, it was power of 1. So here an squared will tell you straight away it's a quadratic sequence. So why this formula is important is that if you're given a sequence and you're asked to find the T of n for it, you will have to figure out if it's quadratic by subtracting or dividing the terms and finding that the second difference is constant, and then you know you're using your it's an arithmetic, so you'll be subtracting them from each other. So if you find that the second differences are constant, you will refer straight to that formula and you will start plugging in your values. So a note to remember, which is really important, everyone forgets it, they remember the formula but they forget the most important thing, which is that A being your first term, in this quadratic sequence, A is always half of the second difference. So if you discover that your second difference is 4, then your A for this quadratic term, or the A in this term an squared plus bn plus c is going to be 2. So that people forget that, okay? Now we go to example 9. So example 9 here, we have a sequence 4, 6, 10, 16, and the pattern is continued. And they want you to verify that the sequence is not arithmetic. Very easy, subtract one from the other and see if the first difference are constant. Show that the sequence is quadratic. Again, separate them or subtract them from each other, and go and do it for the second for the first difference, subtract the first differences from each other. And if you find that the second differences are constant, well, you've got a quadratic. And then if the general term of this sequence can be written as T of n is equal to an squared plus bn plus c, find the values of the constants a, b, c. So what I've done is I've just written out the terms there. And let's do very quickly, what's the first difference? 2, 4, 6. As we can see, not constant. Okay, so it's not arithmetic. Let's do the second difference. 2 for 4, 2, 4, 6, 2. So we have constant. Okay, immediately you know it's quadratic very quickly. If you even do that much in the exam, you've got a good chunk of the points. Right, now we know that it's constant. We now have to find the values of constants a, b, and c. In other words, we have to write out the general formula of this term. But we don't know b and we don't know c, but we do know a. So we move this up a bit. And as I said previously, what did I say about a? A is equal to half of the second difference. So straight away we have a. So a is equal to half of 2, which is equal to 1. Okay. So what's the next part? We know then we substitute in, we have T1. We know what it is. What's T1? It's 4. T1, T2, T3, T4. So we know that T1 is going to be 1 plus B plus C is equal to 4. So B plus C is equal to 3. And we know that T1 was equal to 4. That's where that came from. Okay. For T2, we know that it's equal to 6. So we have 1 times 4 plus B times 2 plus C is equal to 6. This gives us 2B plus C is equal to 2. So that's your next. There you go. You've got 2 equations in 2 variables, B and C. So I'm not going to do it, but you can solve simultaneously yourselves, and you will get a T of n is equal to n squared minus n plus 4. Because when it's solved, we got B is equal to -1 and C is equal to 4. So this is the important part here. This is the stuff that you need to know. How to sub in. Remember, the A is equal to half the second difference. Can't emphasize that enough. And then you already have some of the terms, T1, T2, T3, T4. So slot in what information you know.
Sorry, Suzanne, got a question coming in from a student here.
Yeah.
Why do you multiply the A equals a half by 2?
Because the second difference is 2, remember? The second difference is 2, and the formula that the note I gave you in the slides was, remember, with quadratic sequences, A is always equal to half the second difference. It's something that helps you solve them. So then I said here, A is equal to half by 2, which is equal to 1, and I slotted it in here straight away for A. So I hope that answers your question. Okay?
That's great. Thanks, Suzanne.
Now, let me just go back. We've done question 9. So again, that's it highlighted there again for you, the person who asked the question. Those are the two important notes you need to remember for solving quadratic sequences. T of n is equal to an squared plus bn plus c. You're not going to know a, b, or c, but you are going to know the values of different n's because you'll be given some terms. So you slot them in, and you won't know a except that it's a is equal to half the second difference. So you have to remember that. Everybody that I work with forget the a is equal to half the second difference. So now we'll move on to geometric sequences and series. And the definition of a geometric sequence is one in which every term after the first term can be constructed from the previous term by multiplying or dividing by the same fixed constant. And that fixed constant is called your common ratio. For example, we have 2, 6, 18, and 54. So if you have a look at that and you think, if you divide 6 by 2, you get 3. If you divide 18 by 6, you get 3. If you divide 54 by 18, you get 3. So now we're discovering that we have a constant ratio. It's the same ratio. So there's a constant ratio between successive terms of the sequence. So the example is if you divide t of n by t of n minus 1, which is the term right before it, you'll get a constant. Again, for all n greater than or equal to 2, that's just to make sure we don't get a t0. A sequence is geometric if it can be written in this form. T of n is equal to p times q to the power of n, where p and q are constants. So if you have a sequence and you can write it into that form, if you can get it written in that form, you know it's geometric. So for the general terms, you have the first term again is going to be a, which is t1. The common ratio is r, and the formula for it is t2 divided by t1, or tn divided by tn minus 1. And the formula for the actual sequence is t of n is equal to a by r to the power of n minus 1. So we have an example here. Show that the sequence given by the formula t of n is equal to 3 by 2 to the power of n minus 1 is geometric. For this sequence, find the first term and the common ratio. So we're looking for, what are we looking for in terms of letters? So what are they looking for first term? So they're looking for a, or actually we're looking for t1, and the common ratio is r. So the solution for that is we have t of n is equal to 3 times 2 to the power of n minus 1, and likewise t of n minus 1, because we want to divide t of n by t of n minus 1, and we have the formula for t of n, we can just substitute in n minus 1 in wherever there's an n, and we get t of n minus 1 is equal to 3 by 2 to the power of n minus 1 minus 1. We're just substituting in n minus 1 wherever there's an n, okay? So that gives us 3 to the power of 2, 3 by 2 to the power of n minus 2. So we know that the common ratio, which is what we're trying to find, is t of n all over t of n minus 1. In this case, it's going to be 3 times 2 to the power of n minus 1 all over 3 by 2 to the power of n minus 2. So our 3's go, easy enough. And we are left with 2 to the power of n minus 1 all over 2 to the power of n minus 2. And you should remember this from the recent logs, that that is equal to 2 to the power of n minus 1 minus n minus 2. Okay, remember, if you have a to the power of n divided by a to the power of, we'll say, b, that's equal to a by a to the power of minus b, because if I brought that up, right? And that is a to the power of 1 by a to the power of minus b. So that's equal to, you add the powers if you multiply them. So it's a to the power of 1 minus b. Okay? That's just a little log aside that you should remember to do. That's how we got 2 to the power of n minus 1 over 2 to the power of n minus 2 as 2 to the power of both powers, one power subtracted from the other. And that's equal to 2 to the power of 1 is equal to 2. And we know that's a constant. So it's a constant ratio. Okay? So the constant ratio R is equal to 2. So we know it's a geometric sequence. Okay. Now we also have A is equal to T1. First term is equal to T1 is equal to 3 by 2 to the power of 1 minus 1 is equal to 3 to the power of 1 is equal to 3. Remember, we're taking it from our formula, which is 3 to the power of 3 times 2 to the power of n minus 1. So again, we just substituted in 1 for our n, and that gave us our first term A. So we got R is equal to 2 and A is equal to 3. Now this is where it gets complicated, guys. I want you to be very careful here, and it gets tricky. They're calling A the first term here. For this sequence, find the first term and the common ratio. We know the first term of every sequence is A, but be careful with the use of A, because, for instance, with the quadratics, you have A plus Bn plus C, and in the formula for T of n, you have AR to the power of n minus 1. So you have to be careful with the A's, what they're looking for. Oh, 11. So I want to do 11 as well. On to 11. So geometric sequence has a third term of 48 and an eighth term of 373,248. Find the value of the sixth term. So that what do we know? We know that T of 3 is equal to 48. And we know that T of 8 is equal to 373,248. But we also know the general term for the geometric sequence is A or the power of n minus 1. Okay, so that means T of 3 should be A or squared, and that's equal to 48. And for T of 8, that should be A or to the power of 7, and that's equal to 373,248. So if we divide A or 7 divided by A or squared, what will that give us? it could give us 373,248 divided by 48, and that implies that the R's go, or the A's go, so we're left with R to the power of 5 is equal to 7776. So R is equal to 6. Simple as. So the trick in this question was equating the term, the formula to the number. The formula to the number. And then you're able to use algebra to solve for R. So the next part is find the value of the sixth term of this sequence. So the sixth term, we have t of 6 is equal to a r to the power of 5. Now, have we solved for a is 36? So we need to solve for a, because we've solved for r and we don't know a, and we need that to solve t of 6. So what's a? Well, we know that a r squared is equal to 48. Just take any one of these formulae. And that means a by 6 squared is equal to 48. So a is equal to 48 over 36. So that gives us 4 over 3. So now we have our a as well. So that gives us 4 over 3 by 6 to the power of 5. And that gives us 10368. Okay. So the sum of terms is the next thing to do with your geometric sequences. You have the sum of terms is, the formula is again in your tables, a by 1 minus r power of n minus 1 all over 1 minus r, where r is not equal to 1. Let's say here, example 12. So example 12, so we're asked to find a formula for S of n for the geometric series. In other words, what they're saying is this formula doesn't necessarily, no, forget what I just said. So we have find a formula for S of n for the geometric series, a half plus 3 over 2 plus 9 over 2 plus dot dot. And then find the value of n if S of n is 1640. Okay, so for the series, we have, what we have, a is equal to what? A is the first term, remember. A is equal to a half. And r is equal to what? Well, if you divide 3 over 2 divided by a half, you get 3. So there's our constant ratio. And our formula for S of n is, pop it all in, a by 1 minus r to the power of n all over 1 minus r is equal to a half into 1 minus 3 to the power of n all over 1 minus 3 is equal to 3 to the power of n minus 1 all over 4. That's your formula, is equal to. That's what they want from you. You can't simplify it any more than that. That's your answer. Okay? Part 2. Find the value of S of n of n. So they're not looking for S of n, they're finding n. They want us to find n. So they've given us the answer to the sum, which is 1640. So that means a by 1 minus r to the power of n all over 1 minus r is equal to 1640. And we're trying to solve for n, right? But we already know a and we already know r. So that implies that we have 3 to the power of n minus 1 all over 4 is equal to 1640. That's coming from the formula we solved. Okay, so 3n, just manipulate it, do a bit of algebra. 3 to the power of n minus 1 is equal to 4 times 1640, and we get, I'll do it quickly, 3 to the power of n is equal to 6561. What do you do when you get to here? You need to solve for n. So what do? You get the log of both sides. So n is equal to the log to base 3, remember, go back and check your logs, of 6561, and that's equal to 8. So we know that find the value of n if s of n. So in other words, the sum of the terms up to term 8 is 1640. Okay. So we move on to infinite geometric series. Again, comes up in the exam questions a lot. So your infinite geometric series is of this form. A is your first term, A by R is your second term, your third term is A by R, which is AR squared, and so on. But an infinite geometric series has no last term. It just keeps on going on and on. So some have a finite sum. In other words, they actually do add up to something at the end, and that means it's convergent. You could be asked about a convergent series and a divergent series. So the sum, the term for it is a sum to infinity if it has a finite sum. And it's also if or is greater than -1 and less than 1. In other words, it has to be a fraction. So when R is a fraction, it's going to get smaller and smaller and smaller. And I just want to give you a visual explanation of what a convergent looks like, so you can understand what it means. Here, so this is a geometric convergent series. And if you look at the purple box, it's a half by a half in size. So if you look at the next purple box, it's smaller. So what was it multiplied by to get to that size? Well, a half by a half gives you a quarter. So the constant ratio there is a quarter. So the next box is, so a quarter then is multiplied by a half, and that gives you 1/8. So you can see the boxes get smaller and smaller and smaller and smaller till they go up to the top right hand corner to the tiniest dot. So it does come to a point, whereas and it gets so small that it does actually hit a point, and that's called a geometric convergent series. So it converges downwards into a small point. So it does have a limit. That's important for you to understand. Okay. So if R is less than or equal to -1, or R is greater than 1, in other words, it's not a fraction. It's either, A by R is a big number. And remember now, it's being squared and cubed, so the power increases all the time. So then there's no finite sum, because what's happening is your terms are getting bigger and bigger and bigger and rising to infinity. So that's called a divergent series. And it has no finite sum. So the formula for the sum to infinity, when you have a finite sum, is excuse me, a over 1 minus r. Again, only if r is less than -1 or 1, that means only if r is a fraction. I need to see it, what it means. It has to be a fraction. And if something is a fraction and it's being multiplied by another fraction, obviously it's going to get smaller and smaller. So we go to example 13. So the sum of the first two terms of a geometric series is 9. The sum of the first two terms is 9, and the sum to infinity of the series is 12. If the series has a positive common ratio r, it has to have if it's a geometric series, find the value of r and the fourth term of the series. Okay. Let the first term of the series be a as usual. So we're going to have t1 plus t2. Well, we know that already to be 9. Remember, the sum of the first two terms is 9. So we know that t1 plus t2 is equal to 9. And we also know that that is the equivalent to a plus a r is equal to 9. And if we take a out, that's a times 1 plus r is equal to 9. Okay, so just park that for a minute. That's an equation in two variables. Now we go to the sum to infinity, which is 12. The sum to infinity of the series is 12. We also have a formula for that. So a all over 1 minus r is equal to 12. Now see how we're generating two formulas, equations in two variables, a and r. So that means a is equal to 12 into 1 minus r. Putting 2 into 1, so what we do then is we substitute, so this is 1, we'll say, and this is 2. We substitute in this value here for a into this, we get an equation in just a single variable, which is r. So for instance, we'll do 12 times 1 minus r by, so we're putting that in there, by 1 plus r, and of course that's equal to 9. So this is what we've just done here, 9. So 12 by 1 minus r squared is equal to 9. 12 minus 12 r squared is equal to 9. So 3 is equal to 12 r squared. So basically r is equal to a half, and r is greater than 0. Okay. Then we have a is equal to 12 times 1 minus a half, which is equal to 6. Because we now have a value for r, we can slot it in here into this. And that gives us a is equal to 6. Now the next part of the question was to find the fourth term of the series, which is find T4. Happy days. T4 we know of a geometric series is always a r cubed. We have both of them. We have r is a half and we have a is 6. So we have 6 by a half to the power of 3 is equal to 3/4. Okay, that's your answer there. Right, recurring decimal for the last part. So the last page of the slide. So the recurring decimals, what are they? You definitely see these in the exam question. A recurring decimal is a decimal number which contains a group of digits repeated to infinity. So anytime you see a dot over a number, it means that's repeated to infinity. So you have 3.2, 517, 517, 517. So just remember that the 517 is apologies. So remember that the 517 is the part that's repeated. The 3.2 isn't. So every recurring decimal can be written as a rational number in the form of P over Q is an element of Z, where Q is not equal to 0. Why is Q not equal to 0? Because you can't have a 0 under the line. If you have, it's indefined. So an infinite geometric series, it can be used to write any recurring decimal in a rational form, and that's a very common exam question. Give you a recurring decimal, and they say write it in a rational form. And we go to our final example in this. We go to 14. So by forming an infinite geometric series, write 4.25 dot equals 4.2555 in the form of P over Q, where P and Q are natural numbers. So what we do first of all is we can write this in terms of fractions straight away. How do we know what it is? I mean 4.2555. Well, 4 can be written as 4 plus, so 0.2 is what? It's 2 over 10, isn't it? Yeah. Plus what? That's 5 over 100, plus 5 over 100, plus 5 over 1,000, plus 5 over 10,000. Okay, and so on and so forth. There's your 5 repeating. So if we just have a look at this section here, this part here is our geometric series. And remember, you call it a series when they're all added together. It's just a sequence when they're side by side. Okay, so these two don't form part of the sequence, but they do form part of the number. But what we can do is we can easily write this part as a fraction. We've got to work on the geometric series part. So what's the A in this geometric series? Well, A is 5 over 100. What's R? Well, R is 1 over 10, because each one of them is multiplied by 1 over 10, because this term here would be 5 over 100 by 1 over 10. This would be 5 over 100 by 1 over 10 by 1 over 10, which is typically A R squared, A R and A. Okay? So, and as we know, R is less than 1 and greater than -1. In other words, it's a fraction, is it? It is. R is a fraction. Now that tells us that we have a finite sum. So the sum to infinity of it is A over 1 minus R. And we're using this to find the value of what's in the square brackets. Okay, so then we have 4.25 dot is equal to, 42 over 10 for this bit here. 4 plus 2 tenths is 42 tenths. Plus, we're going to do the plus s to infinity, okay, which is equal to 42 over 10 plus A over R, which A over 1 minus R, which is 5 hundredths all over 1 minus 1 tenth. Okay, this is our A over over. And that is equal to 21 over 5 plus 5 over 100 minus 10. And that is equal to 383 over 90. And that's your sum to infinity. That's your answer. Can't break it down any more than that. Okay, so what was key here was that once you established that your R was a tenth, was a fraction, i.e. this part here, it satisfies that, you could then use sum to infinity because you knew it had a finite sum. And that's something you could be asked quite easily as a question in an exam, confirm whether it has a finite sum and explain why. And so there you have your formula for sum to infinity. So don't be afraid of limits. Most students that I deal with hate limits of a sequence and they run from it and think it's too hard. It's not that bad. You should just follow your main rules and use your sum to infinity, and you'll be fine with that. Okay. So for any of you that are still with me, I want to thank you very much for your attention. Unfortunately, the lecture ran on due to technical issues. I didn't get to put up a lot of exam questions. But what I am going to do now is I'm going to go back to the whiteboard and flick through each page slowly so you get to see all the workings that we did all in one place. So at least you only have to go to the end of the video if you want to do your examples. So another thing I just want to let you know is that all the information that I use today is based on these books called Maths Extra. And they're written by Aidan Rowntree, and they're really, really good books because what he has designed the handbook for is to improve your exam grade in the Leaving Certificate paper. He's got a book one, he's got a paper one, he's got a paper two. And I do find that it cuts through a lot of the bulk of text that you have in your textbooks, and he just gets to the crunch, as in the main formula that you need. He gives you different examples that test your knowledge, and I just find them really good. But you don't have to purchase them. You can purchase them. They're about, I don't know, they're not expensive, about 7 or 8 quid each. But you can also get a free book, a free ebook. They're available as a free ebook online at www.cjf.ie/code. And I would highly recommend them. I find them excellent for they cover every topic. So if you bear with me, I'm going to switch over to the whiteboard and go back to the beginning and just flick through each one slowly. Move this down. Thank you, Eamon.
Thank you, Suzanne, for a great presentation with loads of examples and questions done there. And that was a great idea to put the whiteboard up in the end so that students can replay or pause when they watch the video. They can pause where they want to have a look. So that was a great presentation. Don't forget the students that there's information on page 22 of your log tables about sequences and series. And it's a topic that is actually, if you put a little bit of effort into it, you can get fairly good marks in this question in the Leaving Cert paper. So have a look again, as always, at the examination, at the past papers and examinations.ie, and have a look at the Khan Academy for some more resources to help you with this topic. So I think that's all for now, and see you next week for the statistics tutorial. Okay, so bye for now.